Hi everyone, welcome to this supplementary video. So this video is focusing on buoyancy forces and specifically on Archimedes principle and pressure forces. This video will be a little bit more complex in terms of calculations, as you will see. And the idea is to give you practice of a slightly more complex problem than you will do in your class. Homework 2 problem 3 is related to sort of this idea here, parts of it. Obviously, that is not on buoyancy forces, it's on more on pressure forces. But here we'll be calculating pressure forces to finally calculate the buoyancy force. So that's why this will also help you with that problem. So let's look at the problem and then I will try to go slow. There is some sort of vector math involved in this problem. Hopefully you can follow along and it'll be slightly longer video, but hopefully it will help you. So the problem essentially focuses on sort of this triangular block that is present inside water fully. Okay, so there is this triangular block. As you can see, there it has all the sides are A. So it's an equilateral triangle like this. Okay, A, and A. And even within the plane, it has the same sort of dimension A. So every dimension is A. And what really the problem is trying to do is asking you to calculate the force buoyancy force. So as you will do in your homework 2 problem 2, you don't have to do much about using Archimedes principle. Archimedes principle simply says buoyancy force FB is upwards positive. So let's define this X, Y, and Z. So it will be in the K cap direction. So buoyancy force is weight of the fluid displaced, right? So weight of the fluid displaced. And then it is in the positive K cap direction. And so we have to find basically the weight of the fluid displaced by this block. We know the density is, let's say, rho, right? And then rho times volume. So what is the volume of something like this? Is we have to take the volume of this block. So first, what you can do is you can do the area of the triangle, right? So you can take the area of the triangle times A times G K cap. So this is the area, and the other is the depth, right? So that's the depth into the plane. So you can simply just take that because it's throughout the whole into the plane direction, it's A. So you can simply do this, or you get area of the triangle of an equilateral triangle. What is that? Hopefully you can remember this. It's root 3 by 4 A square times A times G K cap. Or you can say this is rho G root 3 by 4 A cube K cap. Or you can simply say root 3 by 4 gamma A cube. Okay, because rho G is gamma. So this is simply the Archimedes principle. You get this answer, and for most practical problems, this is sufficient for your any homework problems or anything like that. Now, the second approach that I want to do is the pressure force. So we did this also in class, is that this force has to be equal to the net pressure force, right? And that's more complex to calculate, but we will do that in this just to show you how to do it. So F buoyancy in this case is net F pressure force. So the net pressure force is the pressure force acts on surfaces. Okay, so we have discussed this. Pressure force act on surfaces. So we have 5 surfaces, right? So there are 2 like these surfaces. So I'll mark them with this color here. This one, and then there is the front and the back, and then there is the bottom. Okay, there are 5 surfaces. So 2 inclined, front, back, and then the bottom. Remember that pressure force always pushes. So we'll have a pressure force pushing from the front and the back, and like we had done in the homework problem, in the class problem, if you're making that force from the front and back, they will cancel each other out, right? Because they're going in the front and back. So I will say, let's say we have this, right? Something like this, and I'll just come to this. So we have F front plus F back plus F left plus F right plus F bottom. Okay. There is no top face because it's a triangle, so it's not, there is no top face. So what I'm saying is combine, both go to 0 because the front and back cancel each other out. Now, would the left and right cancel each other out too? So that is a question that you have to think. You can argue that they are equal in magnitude, but note that they are not equal and opposite in direction. So what I'm trying to say is this is F left and F right, right? So on these two inclined faces, and I'm not sketching the direction into the plane. So hopefully you can visualize that the force is acting on sort of this surface here. This is the surface we're talking about, and same here. Okay. So these two surfaces here and here. And so when you take F left, you will basically get two components out. Maybe let me sketch it with a dotted. Like this, and then F right will get. So there will be two components, one horizontal, one vertical, because it's an inclined surface. It's normal to the surface, it's an inclined surface. So the horizontal portions will cancel out, but the verticals will not cancel out because they're both pointing in the same direction. So in an inclined surface, as you can see, it's more complex because now the side faces are also contributing to the net pressure force. Okay. So now if we do the pressure force, we remember that when we do F left, F right, and we'll calculate these pressure forces, and F bottom. To calculate the pressure force, we have to focus on whether we have the pressure, constant or pressure varying. So what's happening to the pressure at the bottom face? Okay, so first let's focus on this. On the bottom face, the Z is constant, right? It's vertically, it's just, one height. And so the pressure is constant. So I can simply cite pressure times area. So I can say P bottom times area. This is A bottom. So simply this pressure times area. And so the pressure at the bottom, and we have to now do some trigonometry as well, is the height. So we have to first go from here. This is point P ATM, then this is height H. But I don't have to stop here. I have to go all the way down here. And to go all the way down here, I also have to travel this vertical distance. Okay. And note this is not A. This is a vertical distance. This angle is 60 degrees. This is an so remember hypotenuse, base, and height. So to get from hypotenuse to height, you get multiplied by sine. Okay. So essentially you will get sine 60. So A into 3 by 2, which is sine theta in this case. Okay. So at the bottom pressure, you get the height pressure to be P ATM plus gamma H plus A square root 3 by 2. Okay. And maybe it's just easier to do this. And A bottom is this whole surface here. So it has A n times A, right? It's just a simple rectangle. So it's A times A square. So you get A square. Okay, so this is, and then the direction has to be pushing. So it's pushing the block up. So pressure is K cap. So the direction is K cap. So that's the P bottom. So hopefully this makes sense. This is generally the easier part of this. It is similar to what we have done. The only difference being that now we have this square root 3 by 2 factor coming in because of the fact that we have to take the height of the triangle, not the side. Sides is inclined. Okay. Now let's focus for now on the left side now. Okay, so left side, it's at height H down. Okay. Now the problem in calculating the F left is the fact that the confusing part comes from the fact that you don't have you're obviously changing the Z. If I'm going along this direction, my Z is changing or my vertical distance is changing. So what do I do in that case? Much like the class problem which we did on a block, you basically on the pool on a vertical surface, you integrate. Okay, so you integrate, which makes sense because the pressure is changing. So you take a stripe like this, okay, and you integrate from there. Okay, so I will make the direction T from 0 to A, T going from 0 to A. But note that my pressure for any given T is not necessarily this gamma P18 plus gamma H plus T. Pressure at any point T here like this, but again you need to take this sort of sine part, right, theta, because the vertical distance is still not just gamma H plus T. So what I'm trying to say here is you will get P ATM plus gamma H plus T square root 3 by 2. Okay. Then now distance area is that strip. Okay, that the strip that is dt times A 0 to A. It's very important to understand this. This is very important. Okay. So what have I done here? First, note that I'm taking the pressure again. Pressure at this point, so think of it like this. At this point, the T is this part is H. Okay, this part, vertical part is H, and this part is T. So to get this distance, I will essentially have to do a sine 60, right? This part is T sine 60. So that's why I get a T square root 3 by 2 dt by A. So that's how I get the full left for the magnitude. I get this answer. But by the way, this is still not finished because I have not multiplied with the direction. Because I cannot just simply say I know the direction is like sort of inclined. The direction is some n cap, which we have not defined what n hat is, or so we'll discuss this in a second. Okay, so first I hope this is clear. Let's do the integration. We get P ATM times A square plus gamma times H into A square as well. Okay, and then I have T square by 2. T dt is T square by 2. So if you do that, you will get gamma into root 3 by 4 root 3 by 4 A cube. Okay, and this direction is n cap. Okay, and which I have not defined what n is yet. Okay, so this is a more complex integration, but please take your time. Understand is very important. The only thing I'm doing more complex here is that the distance that I'm taking T has now, I have to take the height as T sine theta. That's really all there is here. This is T sine theta. Okay, and then after that, hopefully it makes sense. Now, what is this n cap? To think of this n cap, remember that I have to do a pressure which is pushing. Okay, so that's very important to understand that the pressure is now pushing. And so this angle is theta. And this is a small fact that I've never forgotten. I learned this way back in my undergrad, is that if a line makes an angle theta with the horizontal, the normal to it makes an angle theta with the vertical. Okay. So you can always, a lot of students get confused with trigonometry. Just remember this. This inclined line is making angle theta with the horizontal, but when now I have something perpendicular to it, it will make theta angle with the vertical, which makes sense because I've just rotated the whole thing by 90 degrees, right? So it will make theta with the vertical. So if this is n hat, then in the minus direction, it will be a cos theta. Again, I'm taking a base. And in this direction, it will be a sine theta. So what I'm saying is, this essentially becomes root 3 by 2 I cap minus half k cap. Okay, so that's my direction. I'm taking sine theta I cap minus cos theta k cap because it's in the negative direction. So what you are essentially getting here is you are getting the answer P ATM A square plus gamma H A square plus gamma root 3 by 4 A cube into root 3 by 2 I cap minus half k cap. Okay, this is my first step. Now, F right, I don't have to calculate. F right is simply the same number as we had discussed, but the direction is opposite. F right, when I will do, I will have both to be negative. My I cap would also be negative and J cap would also be negative. So I can simply write it's the same part, P ATM A square gamma H A square is gamma root 3 by 4 A cube minus root 3 by 2 I cap minus half K cap. So the magnitude stays the same, but the I cap, which is the X component, is the opposite, and the Z component remains the same because they are both pointing downwards. So now if I do the full sum, FB, F left plus F right plus F top. First, I want to show that it's very obvious that because we have that's the way we have taken, the I components gets cancelled out, right? So the I component get cancelled out. So I'll just copy paste this part first here. Okay, so this is the F bottom. So I have written on top by mistake, it's F bottom. Okay, F bottom here. And so this is the part that I get here on the K cap. Let's move it here. Then from here, from this part, I get PATM from the left, PATM plus gamma H A square plus gamma root 3 by 4 A cube into minus half K cap. This part, and then F right will also be the same, right? Minus half PATM plus gamma H A square plus gamma root 3 by 4 A cube K cap. Okay. So three parts, the side had cancelled out already. So now let's sum them because everything is in K cap. I can just sum directly. First things first, note that this gets cancelled out, right? PATM gets cancelled out. Minus half becomes minus PATM, and then PATM gets cancelled out. Then note that I also cancel out this gamma HA square, right? Because I get minus half gamma H minus half gamma H. Then here I'm saying I have minus gamma root 3 by 4 A cube, 8 A cube K cap, minus gamma root 3 by 8 A cube K cap, and plus gamma root 3 by 2 A cube K cap. Okay, and so from here, if I sum them, this becomes minus gamma root 3 by 4 A cube K cap plus gamma root 3 by 2 A cube K cap. And finally, this becomes gamma root 3 by 4 A cube K cap. Okay, and this is the same answer as the Archimedes principle. So this is really beautiful to see this like result. I have always really liked this result. As you can see, it is exactly the same as the weight of the fluid displaced, root 3 by 4 gamma K cap. It's a lot more complex calculation, but it's very instructive. First, you learn that left and right inclined faces contribute. So there is a net negative Z force that comes out, but it gets balanced just about the right amount. They cancel out the X components. And mathematically, you also learn how to integrate, more over inclined surfaces. So some hint of this is in the homework to problem 3, where you have an inclined surface. So you will follow a similar approach. So hopefully this also helps with that. And it also helps you clarify the concept of Archimedes principle and buoyancy force. So hopefully this video was helpful. You can let us know if you have any questions, and I look forward to seeing you in the lecture.